All right.
Very good. Yeah, so we will have 3 talks today. Welcome everybody. And all talks today will be by graduate students, and there'll be a very tight schedule. So yeah, with no breaks. So just get started. And so let's start by introducing Huanhuan Yu, who will speak about Beilinson Drinfeld Schubert varieties of parahoric group schemes and twisted global Demazure modules. Please go ahead.
Okay, thanks for the invitation and thanks for the organizer. Today, let me introduce myself first. My name is Huanhuan Yu. I'm a 5th-year grad student in UNC at Chapel Hill. Today, I'll talk about the Beilinson Drinfeld Schubert variety of parahoric group schemes and twisted global Demazure modules. This is my joint work with my advisor, Jiuzu. Okay, let's start from the finite dimensional case. Let G be a simply connected semisimple algebraic group over C. For example, the group GON, and we fix a Borel subgroup and a maximum torus T inside the Borel subgroup. We can define a flag variety G quotient B. For example, when G is GON, B is the group of upper triangular matrices, T is the group of diagonal matrices. Then there is a bijection between the G quotient B and the set of flags of the n-dimensional space C, and that's why we call it a flag variety. And let U be a unipotent radical of the Borel subgroup B for any weight mu, which is a map from the maximum torus to C star. We can extend this map to a map from Borel subgroup to C star. I denote by tilde mu. This is the composition map. B maps to B quotient U. It can be identified with the maximum torus T, and then T maps to C star. We denote by C sub mu the one-dimensional B module generated by one vector V. This is a B module given by defined by this action. The Borel subgroup act on this vector V with the map tilde mu. And then we can define a line bundle on the flag variety G quotient B. This is a line bundle over the flag variety G quotient B. It is G times the one-dimensional B module over the Borel group B. This is a line bundle over the flag variety G quotient B. Then we have a Borel theorem. It says that the space of global sections of the line bundle L mu on the flag variety G quotient B is isomorphic to the dual of the highest weight representation V of mu of highest weight mu. Okay, any question? This is the finite case. And moreover, for this group G, we have a Bruhat decomposition. Here, W is the Y group of G. This induces a decomposition of the flag variety into B orbits. G quotient B is the disjoint union of BWB quotient B. This is a B orbit. You can think B act on this flag variety. This is a B orbit we denoted by X sub W. It is also called Schubert cell, and its closure is called a Schubert variety. For the highest weight module V of mu, we can define a B submodule inside the V of mu. It is the UB span of the vector V sub W mu. Here, the V sub W mu is the vector of weight W mu. Here, W is in the Y group. This B sub module is called a Demazure module. And we have a isomorphism. The space of global sections of the line bundle on the Schubert variety is isomorphic to the dual of the Demazure module. Okay, these are the Borel-Weil theorem in the final dimensional case. It has analogues for affine Schubert variety. Let G be a simple real algebraic and a capital G be the adjoint group of G. We can define affine Grassmannian of G to be the quotient G of K, quotient G of O. Here, K is the ring of Lorentz series and O is the ring of formal power series. I denote this affine Grassmannian by G sub G. We fix a maximum torus T in the group, in this group, adjoint group G. For each dominant co-weight lambda, we can define a point in T of K. This is the image of T under the map from K star to T of K. And for this point T to lambda in T of K, we denote by E to lambda the associate point in the affine Grassmannian G sub G. And then we can define a affine Schubert cell to be the GO orbit of E to lambda. This is called a affine Schubert cell. And similar to the final dimensional case, this is very similar to the previous case. The affine Grassmannian is a disjoint union of the affine Schubert cell. It is called Cardan decomposition. The affine Schubert cell are parameterized by the dominant co-weight of T. If we take the closure of the affine Schubert cell, we get the affine Schubert variety. And there is a Borel-Weil type theorem due to Kuma and Demazure. We have an isomorphism between the space of global sections of the level 1 line bundle, the cis power of level 1 line bundle on affine Schubert variety, and the affine level C affine Demazure module. I not define the Demazure module here because this is a Schubert variety seminar. We only focus on the Schubert varieties. Okay, any questions so far? This is also the untwisted case. For the twisted case, we have a similar Borel type theorem. We first introduce a group scheme curly G. Let sigma be a standard orthomorphism of order M on G, preserving a Borel subgroup and a maximum torus T. You can just think about the case when G is not A to L. In this case, sigma is defined to be a diagonal homomorphism. When G is A to L, things are a little bit complicated. It is order 4 automorphism. For this standard automorphism on G, we can define its action on the ring of Lorentz series and the ring of formal power series by letting sigma act on T to be epsilon inverse times T. Here the epsilon is a primitive MC-Fluid of unity. And we denote by O bar the sigma fixed point of the ring of formal power series. It is C of T to M. It's just the ring of a sigma fixed point in the ring of formal power series. We define a group skin to be the sigma of fixed point of the restriction of the skin GO to O bar. The definition is a little bit complicated, but here we just want to define a twisted affine Grassmannian of this group skin G. The definition is a little bit complicated, but the basic idea is very simple. The C point of this twisted affine Grassmannian G sub curly G is exactly the sigma fixed point of G of K quotient now sigma fixed point of G of O. In this case, the twisted affine Grassmannian also has a Cardan decomposition into twisted Schubert cells, twisted affine Schubert cells. These Schubert cells are parametrized by the sigma dominant sigma co-invariant of the sigma invariant dominant co-weight of T. This set is the image of the dominant co-weight under the projection map from the co-weight to the co-invariance of the co-weight. Okay. As before, we take the closure of the twisted affine Schubert cell to be the twisted affine Schubert variety, and we let L be the level 1 line bundle on the twisted affine Grassmannian. Similar to the untwisted case, we have a Borel-Weil type theorem due to Kuma and Demazure. There is an isomorphism between the space of global sessions of cis power of level 1 line bundle on the twisted affine Schubert variety and twisted affine Demazure module. In particular, if we allow sigma to be the trivial morphism, the trivial diagonal automorphism, then this group skin is exactly the constant group skin G. So the left-hand side is exactly when sigma is trivial diagonal automorphism, the left-hand side becomes the space of line bundle on the untwisted affine Schubert varieties. And the right-hand side is exactly the untwisted affine Demazure module. This is the Borel-Weil type theorem in the twisted case. These two Borel-Weil type theorem in either twisted case or untwisted case have a global version. That is a Borel-Weil type theorem for Beilinson Drinfeld Schubert variety. Okay, any questions so far? From now on, I'll introduce my work with my advisor, Jiuzu. Okay. I'll skip those definition of global Demazure modules. Okay, we define a parahoric varieties group skin G. Let A1 be the affine line with coordinate T, and it has an sigma action sending P to epsilon P. We denote by A1 bar the quotient line, A1 quotient now the sigma action. It is isomorphic to A1. And let pi be the projection map from A1 to A1 bar.
5 minutes.
Okay. And denote by P bar the image of P under the projection map. We can define a group skin over A1 bar, which is the sigma fixed point of the weight restriction of the constant group skin from A1 to A1 bar. This is a parahoric varieties group skin over A1 bar in the sense of Heinlo's Papa's report. Definition looks complicated, but there is some property that capture this group skin. For any y, which is not zero, the restriction of this parahoric group skin to the formal disk around y is isomorphic to the constant group skin G over the formal disk around y. If y is zero, then the restriction of the group skin to the formal disk around y is isomorphic to the parahoric group skin, the curly G we defined before, the twisted case. For this parahoric group skin G, we can define a Beilinson Drinfeld Grassmannian G AN. This is a collection of triples, a point in AN, a G torsor over A1 bar, and a trivialization of the torsor outside those PI. This looks complicated, but let's just look at the fiber. For each fiber at P, such that the coordinates are in different sigma orbit, then it is just the product of n copies of affine Grassmannian. If Pi is not zero, then GPI is just the untwisted affine Grassmannian. When Pi is zero, then it is a twisted affine Grassmannian. And for this parahoric group skin, we can also define a Beilinson Drinfeld Schubert variety, GAN lambda arrow. This Beilinson Drinfeld affine Grassmannian, Beilinson Drinfeld Schubert variety has a factorization property, and its fiber, when the coordinates are not in the same orbit, the fiber is just the product of n copies of affine Schubert varieties. Okay, this is
2 minutes.
Yeah, this is one last page. This is my result. Let L be the level 1 line bundle on the Beilinson Drinfeld Schubert variety. We have an isomorphism between the space of global section of cis power of line bundle on the Beilinson Drinfeld Schubert variety of parahoric group skin, and the twisted global Demazure module. This is the Borel-Weil type theorem for the Beilinson Drinfeld Schubert variety. Okay. And the untwisted case was first proved by Domansky, Figgin, and Fingerberger. That is, when sigma is the trivial automorphism, we get the untwisted case. It was first proved by Domansky, Figgin, and Fingerberger. In our theorem, we require sigma to be a standard automorphism. That's all. Thank you.
Thank you for a very nice talk.